In this video, we're going to start Chapter 4, Forced Vibrations of Undamped Single Degree of Freedom Systems. So the systems we've considered up to now undergo free vibrations, so no external forces are acting on the system during the motion. These systems have had natural frequencies at which the vibrations occur. However, if an external force is applied during the motion, other vibrations can occur that are not at this natural frequency. An external force can supply energy to the system, driving the vibrations. So the presence of these external forces driving the motion gives us what we call forced vibrations. The forcing function can be harmonic functions, which are periodic, so like a sine and cosine function. They can be other periodic functions that are not harmonic. They can be non-periodic functions, or they can be random forces. So we will start by considering harmonic forces of the form f of t is equal to f naught sine omega t, where f naught is the amplitude of the forcing function, and omega is the frequency of the forcing function in radians per second. So in this chapter, we're going to consider the forced vibrations of a simple spring mass system. We're going to go back and consider the undamped case first, and then in Chapter 5, we'll consider the damped case. Within this, we will also look at a few different specific areas of interest, like the response at resonance, some special cases like forced vibrations due to a rotating imbalance, as well as base excitation. We'll look at the phenomenon called beating, as well as this idea of transmissibility. So in this video, we're just going to focus on introduction of the forced vibrations for a simple spring mass system. So consider a simple spring mass system. Again, we're considering the undamped case, so we just have a spring and the mass, no damper at this point. So this is the schematic, and we've got this harmonic forcing function applied. So f of t is f naught sine omega t. So this is the free body diagram, mass acceleration diagram. And again, we draw everything in the positive coordinate direction. So we've got our acceleration, mx double dot, and then the forces acting on the system, we have this applied force, f naught sine omega t, as well as the force in the spring, which is kx. So this is similar to our vertically oriented unforced spring mass system, but an additional force on the free body diagram is included. So this forcing function, f naught sine omega t. So let's look at the applying our Newton's laws. So sum of forces equals ma, gives us f naught sine omega t minus kx is equal to mx double dot. And we can rearrange this to find our governing equation, which is mx double dot plus kx is equal to f naught sine omega t. So this is similar to the undamped free vibration case, except now instead of a 0 on the right hand side, we have this forcing function. So this governing equation has a non-zero term on the right-hand side, which means that it is a non-homogeneous differential equation. It's still linear, second order, with constant coefficients, but we've got this non-homogeneous term. So because of the non-homogeneous aspect of this equation, x of t is made up of two parts. So the total response is the homogeneous response plus, or the homogeneous solution plus the particular solution. So the homogeneous part of this equation is the same as what we had before. So mx double dot plus kx is equal to 0. We solved this previously, so we know that xh of t is equal to a sine pt plus cosine pt, where again here we're using p, which is the natural frequency of the system. So p is equal to the square root of k over m. It's important to note that the natural frequency of a system does not change if a load is applied. So the natural frequency is not related to the external force that is applied. It's an intrinsic property of the system related to its mass and stiffness. Now we need to consider the particular solution. So xp is the particular solution and depends on the form of the right-hand side. So to find the solution for this, for the particular solution, we assume a solution that has the same form as the right-hand side. So if we assume that the particular solution looks like the forcing function, so with some constant c sine omega t, we can differentiate this twice to get xp double dot. Then we can substitute this into our equation of motion. So we're putting this into the original equation of motion. So x double dot is given here, and our x is here. We can cancel out the sine omega t in each of the terms and solve for the constant c. So we find that c is equal to f naught over k minus m omega squared. So the particular solution was, remember, c sine omega t. So our particular solution is that xp of t is equal to f naught over k minus m omega squared sine omega t. So now our total solution is our homogeneous plus our particular solutions, and we found those two solutions independently, and then we can combine them together. So our total response is then given as this expression here, where the a sine pt plus b cosine pt is the homogeneous solution. It depends on the initial conditions. If we recall, that's how we end up finding our a and our b. And it dissipates in real systems because in a real system we would have some damping present. So we would have a damping term or a decaying exponential in front of this, which means that in a real system this would dissipate over time. So this is known as a transient response. The particular solution is this part here. It's independent of the initial conditions. So you see everything is defined. We don't have any a and b. We don't have anywhere where for those initial conditions to come into it. And it exists as long as the forcing function is applied. So this is known as the steady state response. So in a real system, this part would dissipate, and then after some amount of time, we would be left with just this response. So this is the steady state solution. And in a forced system, we're quite often most concerned about the steady state solution. So now we can rewrite this f naught over k minus m omega squared in a little bit different way that makes things a bit more convenient. So we can factor out the k here, and we know that k over m is equal to p squared, so that means m over k is equal to 1 over p squared. So we can write this as shown here. So the two kind of important quantities that we end up with is f naught over k, which we'll see is the static deflection, and omega over p, which is the ratio of the forcing frequency to the natural frequency. So those are the two kind of important quantities that that go into the steady state response. So we have our response, our total response here, our x. We can take the derivative of this to find the velocity, so our x dot. And now if we wanted to find those constants a and b in the transient solution, we could apply some initial conditions to find that. So this is our from our position response from our x, we can find that b is equal to x naught, and from the velocity we find that a is equal to this expression here. So if we put all this together, we can look at the total response, and we see that this part is the transient response due to the initial conditions. So that is the homogeneous, comes from the homogeneous solution. And then, or this also comes from the homogeneous solution. There was this other part that has, doesn't have the initial conditions in it, but it does have something to do with the forcing function in it. So this is the transient response due to the loading. So when we start up the loading, there's some transient response. And then this is the steady state response, which, as I said, for forced systems, we're typically just interested in the steady state response, because these other, the homogeneous solution in a damped system, in a real system, would dissipate over time. So we'd be left with the steady state response. So if this is the response of an undamped system to a harmonic force. So if this is the applied force, this one up here is the applied force. So it's harmonic with some frequency omega. The response ends up looking like this sort of combination of the homogeneous solution and the particular solution. So this is the steady state response. And then this is the transient the total response, which has this transient response at another frequency kind of over top of it. So in a real system, this would damp out over time, and we'd be just left with the steady state response. So we know that all real systems have some damping, therefore only the particular or the steady state solution is necessary to describe the behavior. There's a bit of an inconsistency here as we are neglecting the transient response because of damping in the system. However, we started out by considering the undamped system. So the reason that we do that is because, as I said, all real systems do have some damping. So the transient response will disappear regardless of the model that we use. For lightly damped systems, the undamped model is of the steady state solution is reasonable, and it is simpler to use. So that's where we're going to start, and then we will discuss the forced vibration of damped systems as we move a bit further. So let's focus on the particular solution for now. So xp of t is equal to f naught over k minus m omega squared sine omega t, which we rewrote in this form. So we can see that this whole term here we can call the amplitude x. So the amplitude of the response is the product of two things, f naught over k, which is delta static, and 1 over 1 minus omega over p squared. So this delta static is the static deflection of the system if our force, f naught, was applied statically instead of dynamically. So if we just applied a static force of f naught, this is how much the system would deflect. And then the this term, the 1 over 1 minus omega over p squared, is a frequency dependent factor. So this is the absolute value of this term is called the dynamic magnification factor. And this dictates how much the amplitude of the response changes compared to the static case by applying the force dynamically at some frequency omega instead of statically. So the amplitude x is equal to delta static times 1 over the absolute value of 1 minus omega over p squared, which we can also write like this. So if we plot this quantity 1 over 1 minus omega over p squared, or the absolute value of that, as a function of our ratio omega over p, we can see what happens to the amplitude of the response. So this is the dynamic magnification factor as a function of this frequency ratio omega over p. So it tells us then how much the amplitude of the system of the response changes as we change, for example, the forcing function frequency. So there are a few important aspects to look at here. So first, let's consider the case where omega over p is much less than 1. So we're in this region here, or in this region in this figure here, where so omega over p is much less than 1. The effect of the dynamic loading is actually very small. So you can see that the dynamic magnification factor goes to 1 here. So just for with some particular, just as an example, if we start with 0 initial conditions, this is the total response of the system. So the total response looks like this if omega over p is very small. So we can plot this here in this figure. The red line is sine omega t, so the forcing function, and then the black line is the x over delta static, so the total response of the system. And so you can see that there's not a lot of effect beyond the applied load, or the applied force, due to the dynamic magnification. So as you approach omega over p goes to 0, or omega over p, sorry, gets very small, this the dynamic loading has a pretty small effect. So when omega over p goes to 0, the dynamic magnification factor actually goes to 1, and this is the static case. So if omega was equal to 0, we would just be applying the load statically, so our dynamic magnification factor would just be equal to 1. Now on the other end, if omega over p is much bigger than 1, then the amplitude of the response approaches 0. So here we're looking at this kind of region. In this region here. So 1 over 1 minus omega over p squared goes to 0. So for example, if we look at some forcing function, again sine omega t, and then we zoom in, we see that the actual dynamic response of the system has a much smaller amplitude compared to the forcing function. So because as omega over p gets very large, the dynamic magnification factor is actually less than 1, and it actually goes to 0. So in fact, for omega over p is greater than anything bigger than the square root of 2, the dynamic magnification factor is actually less than 1. So that's an important kind of piece to note, is that where this graph crosses this value of 1. So anything with omega over p greater than square root of 2 will actually have the resulting amplitude of the system smaller than the amplitude of the forcing function. Another important area to look at is at resonance, when omega over p is equal to 1. So right here, the amplitude actually goes to infinity. So if we look at the dynamic magnification factor, if omega over p is equal to 1, then the denominator of this goes to 0 and the response amplitude goes to infinity. So if we had some sine omega over t, you can see that the response would eventually just continues to grow. And we'll talk about the response at resonance in a bit more detail later on. The other thing that happens at resonance is that the phase changes from in phase to out of phase at resonance. So if we look at this graph here, so up to here, omega over p is equal to 1, it's in phase, and then beyond that, it is out of phase. So let's look at a little bit more detail of what that means. So if this is the input forcing function, f naught sine omega t, and then these two are the response, when omega is less than p, so omega over p is less than 1, the response is in phase with the input forcing function, and when omega is greater than p, it's actually out of phase with the response is out of phase with the input forcing function. And for undamped systems, this phase angle changes abruptly. So for omega over p is less than 1, it's completely in phase, and then at resonance it switches, and then it is completely 180 degrees or pi radians out of phase. So the difference in the phase can be seen in another way by considering the response written in this form, where phi is the phase angle between the forcing function and the response. So we have this is the steady state response, can be written in either of these two ways. So if omega over p is greater than 1, this value becomes less than 0, becomes negative. So we get we can write it as this here. So we're just bringing the negative here and then writing this as the absolute value. So this is equal to negative x sine omega t. So this is, again, when omega over p is greater than 1, so it's out of phase. So this can be written equivalently as x sine omega t minus pi. Now with omega over p is less than 1, this term becomes positive. So we can write it as this here, so we don't have any sort of sign here. It's positive, and then we can still write it in terms of the absolute value. So this is just equal to x sine omega t, which equivalently is x sine omega t minus 0. So you can see that this has a phase angle of exactly pi, and this has a phase angle of 0. So for omega over p greater than 1, our phase angle is pi, and for omega over p less than 1, our phase angle is 0. And that transition happens abruptly right at omega over p equals 1, or at resonance case.